Welcome to part 2 of our interpolation tutorial for GGR 376. We're going to begin by loading some air pollution data for Paris, France. If you haven't already, you may need to load the rgdal library. If you're following on from the first video, it's probably already loaded. But here is the URL, and we're going to download a GeoJSON that has Paris pollution points. The data has 19 observations, and then we have 8 fields. The pollution data is simply labeled PM, capital P, capital M, for particulate matter. Let's visualize this information on a leaflet map, which we just learned about in the first part of this tutorial. Actually, I'll just talk about this first. So here we're using data equals pollution. You don't need to add the data in, but it makes it a little bit clearer. We're adding tiles, and we're going to add circle markers as opposed to the stylized marker from before. And we get this error, and we're not really sure what's going on. And it looks like we've put it at the extreme northern edge of our map, and our points don't make any sense. Now, based on our GIS backgrounds, we are probably thinking that this is a projection issue. And if you're thinking that, you would be right. Leaflet will work in data that's specified as WGS 84, so latitude and longitude. We can check the projection of our data using the @ symbol and then proj for string. And this is our projection string argument, and we can see that it is zone 31, projections UTM. So we have a UTM projected coordinate system. And this isn't going to work with our leaflet map. So we need to create a version of the data, or project it, to the WGS projection, the geographic coordinate system. And we use the SP transform function. We provide it our object, and then we give it the projection information here. And when we run that, and then call that same set of functions to create the map, we get a map that makes a lot more sense here. So what's nice about this is it gives us information about where these monitors are relative to each other, but we can also zoom in and see what is going on with them. And this could be much more helpful if you were doing some investigative, exploratory analysis and you're just trying to understand your data here. Okay. So we will move forward from here, but I just wanted to show you how we can take that information and put it into Leaflet. And just remember to pay attention to your projections. However, when we're doing our interpolation, either kriging, inverse distance weighted interpolation, we want to make sure that we're using a projected coordinate system so that distances are correctly represented across our space. In lecture, we discussed Thiessen polygons. They're a very, very basic, low quality way of interpolation, but it may be useful at some point. Very useful if you're looking at categorical data. That may not make a lot of sense, that can't really be interpolated the same way that other numerical measures could be. And let's just look at how we do this. So it's actually very straightforward to do. So we have a different function, Veroni. That's another term that we often use for Thiessen polygons, and it's in the Dismo library. So we can call the library, call the function, and then create a plot. And when we do that, here is our plot, and these are our Thiessen polygons. Now, you might be interested in including the points with this plot, which would make a lot of sense. Now, I'll be honest, working with the SP plot is not the easiest thing to do. just clean up this script here a little bit, but we can do it. So we have this option or argument in our SP plot called sp.layout, and it allows you to pass in a list, and here we're creating a list with pollution data and then some ways in which we want to stylize our points. So we're going to use this symbol 19 and we're going to color them white. So when we do that, here we have our symbols and we can see where those points are. The capabilities of R and mapping are improving every day, but for very advanced mapping, you may want to kind of export some of your layers and work in another more suitable environment at times. But for the most part, you can create pretty much any type of map that you need. Now, we have a set of values that were observed, but in many times when we're conducting interpolation, we're going to have a set of locations that have not been observed. In my work, this could be air pollution observations, and then we might have the location of people's homes where we need to assign them air pollution exposure, but we didn't observe the data there. So we need to interpolate it. So here I've created some locations that we want to predict within our study area. So we'll read that in again using the read OGR command. And we see that there are 10 observations, and we have no attributes with it at the moment. We can plot this. So we'll plot first our pollution observations, and then we'll add our prediction points with the color red. So very, very basic, but you can see all of our points fall within the boundaries of our observed points. The red ones are the areas we want to predict at. Okay. And remember, for interpolation, we want to be within the spatial boundary of our points. Otherwise, we're thinking of extrapolation. When we're doing interpolation in R, we'll be working with the gstat library. And it contains functions for spatial and also spatiotemporal geostatistical modeling, prediction, and simulations. It's very, very useful library for our purposes for interpolation here. It can conduct both our IDW interpolation, our kriging approaches, and then we can also do cross validation with a set of tools within it. So call that library, load the library in. You may need to install it. And we'll just walk through how we set up IDW interpolation. So IDW is the function name, and we need to give it a formula. For IDW and ordinary kriging, which is what we'll be doing in our tutorial, we give it the value, so what we're trying to predict, the tilde symbol for our formula, and then just by the number 1. Okay. This number 1 is not the exponent for our distance. It's just saying, there's no other variable that we're using in our interpolation. If we were doing something like co-kriging, we would have a different setup for our formula. We then provide our observed data. So this is our pollution points, the locations in which you want to predict, and then you need to specify your exponent, or our k value in our IDW formula from lecture. Here, we will set k equal to 2. And we're going to just save it in an object called pred, short for predictions. And it tells us the outcome from that just says we used inverse distance weighted interpolation, which is good because that is what we are attempting to do. Let's look a little bit at this object. So we can see it's a class of spatial points data frame from the spatial points package, the SP package. The structure of it. We can see that in the data frame component, we have 10 observations, and we now have 2 variables. When we loaded the data in, we had 0 variables. The 2 variables are the same when we do both kriging and IDW interpolation using the gstat package. One of them is var1 pred, which is our predicted values, and then var1 var, which is variable 1's variance. In kriging, we get variance, but when we're doing IDW interpolation, we don't get an estimation of variance. So they're just NAs at the moment. And then we have our other information that's contained within our spatial points data frames. So we can also view a plot of this. So there's our very straightforward plot. And we can see that our values, our predicted values, range from 9.8 up to 21.6. And to create this, we just call the var1 pred variable, which is our predicted values. Now, you could stop here, and you have interpolated values for those points. However, when we're doing interpolation, we want to get an understanding of the model accuracy. And right now, we don't have an understanding of what's going on with the accuracy of our model. And one way we can do that is through cross validation. And the cross validation function in the gstat package is the same for both IDW or kriging, and it's krige.cv. And we can do with that leave one out cross validation or k-fold validation. Okay. The way we do leave one out cross validation is setting the number of folds equal to the number of observations. So you're just if we have 30 observations, we're creating 30 groups and simply putting one observation in each group. When we remove one of the folds or groups, it just leaves the remaining -1 observations for the prediction of that existing or removed observation. So we give it our formula again in this function. We give it the data, the observed data. Notice when we do our cross validation, we are not including our prediction points because we don't have actual values for those, so we can't compare the actuals versus predicted. And the way we can do leave one out cross validation is simply by doing nfold, and we're going to do it equal to nrow pollution. And nrow pollution, what it does is it just gives you the number of rows or number of observations in our data set. So here it's 19. So we run that, and you notice there's this little bar that goes across. It went very quickly because we have a pretty small sample, but if you had a larger one, it might take some time. It just tells you how things are moving along in your cross-validation. Let's just look at the structure of that. So it's a spatial points data frame, and then it has the data frame, which contains the var1 predictions, the variances, which are all NA, the observed values, which is what we would have observed in the field, the residual, so that's the error, which is the observed value subtracted the predicted value. And then in this case, we don't have z-scores, and it just tells you which fold. And in our scenario here, we are doing leave one out, so each observation is in its own fold. We can take a quick look at the data as well. So we have the predicted values, the empty variance, the observed values, and then the residuals. And here you can see the different folds. So we had 19 folds because we had 19 observations. We can plot our residuals using the spplot function and using the residual variable. So this is part of the way. Now, if we recall from class, we had different measures of fit. One of those measures of fit is the root mean square error, or RMSE. Now let's break apart this formula for a second. So we're going to sum up yi, which is the set of observed values, minus the predicted values. So we have done this step, or this step has been done for us in our output of the cross-validation. That is the residuals. So what we need to do to calculate the root mean square error is to square the residual, which will remove the negative values, make them positive, and they'll be squared. Sum them all up, add them together, and then divide them by n to get the mean, and take the square root of that. Okay. So what that looks like is we take our set of residuals, a vector of residuals, so these are our residual values here. We square them, raise it to the power of 2. So now they're squared, making them all positive. We can then take the mean, and we can pipe the mean to the square root function, which gives us a root mean square error of 7.6. Now, if you're going to be doing this a number of times, we have the ability to write functions in R, and we haven't looked at this in detail at the moment, but let's write a quick function for calculating the root mean square error. So here is our final function, but I'll just walk through how we created that. So we'll just give it this name. And we have to tell R that we're going to create a function. And then we need to add arguments. So we'll just give it the simple argument of x. And x will be our vector of residuals. Okay, so our vector of residuals for this example is stored here in our cross validation output, stored in the data frame, and under the residual variable. Okay. So the first thing we need to do is square x, so raise x to the power of 2. From there, we want to sum them up and then divide by n. Or we want to just simply take the mean of those values. Once we have the mean, which is everything within our square root, we can then just take the square root. And the last thing is I need to tell R what I want to return when I call this function. So I want to return this result. And now I've created this function. I'll just delete this and leave the original one. Now what you will notice is here I use kind of the tidyverse style with the piping. Inside of functions, it's often better to exclude pipes because you would need to load a library to make sure we can access those. So I've written it in a little less easy to interpret way, but it's a little bit better for a function. So when I run this, nothing happens, but it stores my function into the workspace of R. So now what I can do is test out my function. So calling my function name, giving it that vector of values, just to remember, this is our vector of values. And when we run it, we get that same value, 7.604. So at this point, what you would probably do is try different values for that exponent. So instead of the power of 2, maybe to 1.5, 2.5, 3, for example. You would run the cross validation. You would calculate your measure of fit. This example, we've used root mean square error. And then you would make a decision about which parameter for k is best. We'll end this video here, and the next one will begin with kriging.